ஏற்கனவே பார்த்ததோட கண்டினியூஷன் இது. ஒரு 2-3 நாளாக விட்டுட்டோம் கண்டினியூஷனு. இப்போ கண்டினியூ பண்ணிடுறோம். Induced delay comparison. இது வந்து simulation result number 2. We further consider the real satellite networks with a non-uniform distributed user density. These networks operate in an integrated space terrestrial mode with multiple ground gateways. In this setup, satellites receive packets from end users and relay packets to the nearest gateway instead of all other satellite nodes as in the previous section, thus avoiding long ISL path that can span half of the network. The satellite gateway links utilize radio frequency links and do not occupy the ISL terminals. The user density distribution is determined by population demographics, and 30 gateways are strategically placed in proximity to user dense regions to optimize the relay process. These satellite receives the data from ground users and forward it to the nearest gateway station through inter-satellite communication in the entire network. The above table lists the average end user delay when user density distribution and gateways are considered. Compared to figure number 12, where all satellites become source to destination pairs, the user delay is much reduced when the gateways are introduced because only the nearest gateway becomes path destination and transmission path becomes shorter. Since the user density is non-uniform and the ground gateways are placed close to the user dense regions, more packets can reach the gateway through shorter paths, resulting in a lower average delay compared to uniformly distributed user case. Thus, the user density weighted average delay is further reduced. By comparing the 3 ASL and 4 ASL topologies, we find that delay can increase by over 60% in the 72x22 constellation, but in 24x66 constellation is obviously a better design compared to other proposals, where the delay increases only 3%, while 25% of ISLs are saved. Figure 13 illustrates an example of a shortest path connecting the Solomon Island and the Hawaiian Island in different constellation configurations. Although the source and destination are the same, the path patterns are quite different. The hop counts of the two paths are 10 for the 72x22 configuration and 7 for the 10 for the 72x22 configuration and 7 for the 24x66 configuration respectively. The two places are far away in the longitudinal direction, and the 72x22 configuration has shorter interplane ISLs. Thus, the two interplane hops are required and details are cast. Moreover, intraplane ISLs in the 72x22 ISL configuration 72x22 configuration are longer. The increased delay will be higher. Figure 14 and 15 illustrates the further comparison of the CDF of delay in the two constellations. The 72x22 constellations suffer from extra deters when the interplane ISLs are pruned. The delay increases remarkably, but if the satellites are reorganized to the 24 cross 66 configuration, the impact of the pruned ISLs on average delay becomes much smaller. Furthermore, the result of the 36 cross 44 configuration in Table 2 indicates that when NP becomes closer to MP and constellation is more regular, the impact of pruned ISL increases, but the degree of the impact is still small. That is, MP is greater than MP. N is always MP is greater than NP is always preferred, and the greater MP, less impact is caused by pruned ISLs. Network capacity comparison. Since the network capacity is affected by the topology and average hops, the network capacity of various scenarios is also evaluated and compared. With the reference of Mao, concluded that the system capacity is inversely proportional to the average hop count over the network. That is, the fewer hops causes higher system capacity. The non-uniform user distribution and gateway placement are same in the above scenarios. The total user demand is set to 2 Tbps. The satellite gateway link capacity is 20 Gbps and the ISL capacity ranges from 1 to 10 Gbps. During the simulation, each satellite calculates the total user demand within its coverage area, which serves as the access traffic for this satellite. Then for the capacity is evaluated using max flow method. At each time step, a maximum flow problem is constructed based on the constellation configuration, ISL connection topology, user traffic demand, ISL, and satellite to ground link capacities. We finally compute the maximum traffic that flows through the all users to the ground gateway across the network, which is then adopted as the system capacity at the time step. The data represents the average system capacity over multiple time steps. Figure 16 shows the capacity may decrease in the 3-ASL topology, but the effects are not as obvious as hop count or delay. The capacity degradation is around 15% when ISLs are fully occupied. When ISL capacity is large enough, the network capacity is limited by the satellite gateway links. In these cases, the remaining ISLs are capable of routing the allowed traffic. Moreover, it is interesting that the various constellation configuration have very similar performance. The 24 plus 66 configuration does not have more obvious advantages than 72 plus 22 configuration. To summarize the simulation result, we find that the 3 to ISL topology may degrade the network performance in terms of average hop count, delay, network diameter, etc. But the degradation is affected by constellation configuration with fewer orbital planes and more satellites per plane. The pruned ISLs have weaker impact on network performance compared to typical well-connected 4-ISL topology. In a real satellite network with multi-gateway and user distribution, the performance degradation is also reduced. In terms of network capacity, when the ISL bandwidth is limited, the 3-ASL topology may further deteriorate the network performance, but the degradation is not affected by the constellation configuration.